Welcome to the first tutorial on in COMAT COTS COMAT 2021. It is on nearest neighbor search techniques. The speakers are Parth Nagarkar, Arnab Bhattacharya, and Omid Zafari. Parth Nagarkar is assistant professor in computer science at New Mexico State University. He works on nearest neighbor problem, approximate nearest neighbor problem, and is interested in building scalable index structures. Arnab Bhattacharya is professor in computer science at IIT Kanpur, and he is also interested in high dimensional indexing and graph querying. And Omid Zafari is PhD student at New Mexico State University, working on approximate nearest neighbor techniques and locality sensitive hashing techniques. So overall, um, the three experts are in high dimensional data and efficient access to it, and index structures which are very difficult to design and use. So look forward to the tutorial, and audience can ask questions anytime, put it in Q&A, and we'll take it from there. Thank you.
Thank you, Kamal. Should I begin?
Yeah, please go ahead. Yeah.
Okay, thank you. So hi, everyone. Welcome to our tutorial on state-of-the-art nearest neighbor techniques. My name is Partha Nagarkar, and I'm an assistant professor at New Mexico State University. I'll be presenting this tutorial with Arnab Bhattacharya, who's a well-known professor at IIT Kanpur, and Omid Jafri, who works with me at New Mexico State University. So let's begin. Let me first give an overview of the tutorial. I will spend some time explaining what the tutorial will be about, and mainly on the motivation of the problem, and talk briefly about how dimensionality plays an important role in the nearest neighbor problem, and also how it applies to this particular conference on machine learning and data mining. And then I will go back and forth with Arnab, who will explain the nearest neighbor techniques for low dimensional data. And after that, I will explain the techniques for high dimensional data. And we will conclude the tutorial on the research challenges that we see should be addressed in the next few years. So as Kamal mentioned, we welcome questions at any point during the tutorial. So please feel free to stop us. We would be happy to discuss any viewpoints and questions throughout the tutorial. So having said that, again, welcome to the tutorial on nearest neighbor techniques. And let's begin on what can you expect from this tutorial. So finding nearest neighbors is a well-known, is a well-studied problem. I will explain the definition of the problem in the next few slides. But the reason or the motivation of this tutorial is that there are many different kinds of techniques for different types of scenarios. So what do I mean by different types of scenarios is, first of all, mainly, as we know, with so much data implosion, that every application has its own data characteristics. They have their own different processing requirements. So this obviously means that there are many techniques to tackle these different scenarios. There is no one size fits all solution for these problems in the nearest neighbor domain. And that is the main goal of our tutorial, is to explain these differences between different techniques, and to show that once you understand these differences, how you can apply, or which technique should you be applying to your specific application scenario. And another thing Arnab and I have tried is to keep the explanation on a very at an overview, so that we do not spend too much time explaining the technical details of these techniques. So we hope that by the end of the tutorial, the audience can basically distinguish between the different data scenarios that they might have, and to be able to choose the appropriate nearest neighbor technique. So at this point, I'm gonna start explaining what the problem is. Again, feel free to stop me at any point. Please use the Q&A chat box to ask any questions, and I have it open here. Okay, so what is the nearest neighbor problem? So assume that you are given a set of points in a database, in a text file, however you want to store it, and a query in a d-dimensional database. The nearest neighbor problem, the goal of this problem is to return the nearest neighbors of this query point. So if this is my query point, the goal is to return if I want 5 nearest neighbors, then these 5 nearest neighbors. So how does this apply, or what are the applications of this? So one common application that many of us use while using our GPS, while using Google Maps and different map applications, is spatial applications. So think about these points in your database correspond to the latitude, longitude data of buildings or points of interest. And the queries correspond to a particular user who is looking for, let's say, nearby points of interest. So again, the user it wants to know that, wants to query that, can you give me 5 nearest points of interest, or 5 nearest buildings near me, or any particular attractions, travel attractions that the user wants to see. So these queries would be nearest neighbor queries. Another application is for a machine learning pipeline or machine learning workflow is consider an image retrieval system. So we all know that deep neural networks are really popular in these image retrieval systems nowadays because of their really good accuracy. So the way that workflow would work is deep neural networks such as AlexNet are used to extract a feature vector for each image in the database. That means that if you give an image to if you have an image in the database, you use the trained AlexNet or some other neural network to extract these features from the image. These features are stored as a vector of numbers, of real numbers. And so in the case of nearest neighbor applications, these points will be each feature vector corresponding to that image in the database, and the query image will be also represented in this space by the feature vector. So once you use these deep neural networks to extract features, if you want to find, if you give an image of a cat and ask, give me images similar to this cat, then internally there has to be a nearest neighbor query that has to be executed in order to find these similar images. So nearest neighbor problem has very diverse applications in different domains. And since it is so diverse, obviously different problems have different characteristics, which leads to many different techniques. And again, that is the goal of our tutorial. So again, given this query image, in order to find these similar images, a nearest neighbor query has to be executed. Okay, so another important thing is while there are many distance measures that can be considered, like the cosine distance, the Hamming distance, and so on, in this tutorial, we will focus on the popular Euclidean distance measure, and all the techniques that we will explain will be focused on the Euclidean distance. Okay. And so again, since this problem has or is a fundamental operation in many diverse domains, especially right nowadays, since we have a lot of data, we need scalable index structures, scalable techniques are required to speed up the processing. And in this tutorial, we want to focus on these different types of scenarios. We will mainly focus on what happens if you are given low dimensional data or high dimensional data, but which is also somewhat correlated to the problem of do you want exact results or approximate results are fine. So if you have a security application, maybe you want exact results. But if you're okay with pictures of a cat of different breeds, for instance, but you might want the answers really quickly instead of waiting for exact results. In that case, you may want approximate results, that a small loss of accuracy is absolutely acceptable for really fast results. And also, one important thing would be, since we are dealing with really large amounts of data, is the index structure, or is that technique completely in memory? That means that your memory should be really big to fit your data and the index structure, or is that data structure capable of on-disk processing, that the data can be on the disk and the index structure can be on the disk. This is really useful if you have data sets in billions of points or images, for to give an example, and you do not have much memory processing. Okay, so we will focus on these three different types of scenarios in this tutorial. Okay, and so why low dimensional versus high dimensional? And the one important thing that at least everyone should know by the end of this tutorial is, as dimensionality of the data increases, many traditional hierarchical structures, like most databases, if you use the popular B+tree, they suffer from the notorious curse of dimensionality. And, sorry? I thought there was a question. Okay, so many traditional hierarchical structures like the B+tree suffer from the notorious curse of dimensionality. And basically what happens is, as the dimensions increases, the data appears to be sparse and dissimilar, and this makes these traditional pruning techniques that B+trees and other traditional structures use, these pruning techniques become really ineffective. And it has been shown that as dimensionality increases, let's say about more than 10 dimensions, even a naive linear scan or brute force search beats these traditional hierarchical structures for really high dimensional data sets. And so how do we distinguish between low dimensional and high dimensional? And nowadays there's also a third category called ultra high dimensional. And so we took the liberty of giving some numbers to these categories. So low dimensional is many is considered to be less than 10 dimensions. So like spatial applications where these points have latitude, longitude, maybe altitude and other attributes. And high dimensional data sets are when you have dimensions around in dozens of dimensions to, we're going to say millions of dimensions. So there is no particular exact number to distinguish between high dimension and ultra high dimensional, but and we are going to consider ultra high dimensional to be something with greater than millions of dimensions. So what kind of applications have these dimensions? So again, low dimensional is, think about spatial data, 2-dimensional data or 3-dimensional data. High dimensional data would be scientific data, as there's a popular data set called P53 that has about 5,000 dimensions, and those are attributes attributes of a mutant gene, I believe. And also multimedia data has very high dimensions, like the feature vectors representing an image that you get from neural networks oftentimes have hundreds of dimensions. In some specific cases, about 900 to 1,000 dimensions as well. So, and again, what are dimensions? Dimensions are simply attributes. Attributes are features. So if I give one point in a database that has multiple features. So for spatial data, one feature is latitude, another feature is longitude, X and Y coordinates. For high dimensional data sets, something similar is the neural network that you are using takes into consideration multiple different factors in order to create this feature vector. Recently, people also do these nearest neighbor queries on text data or social media data. So in here, all the words, let's say, are attributes of a document. In that case, you will have millions of words belonging to a document, and hence millions of features or millions of dimensions. Important characteristic of ultra high dimensional data is that it's really, really sparse. So in this tutorial, we are going to focus on low dimensional data sets and high dimensional data set. And we are we leave ultra high dimensional, which is not as, there is research done on ultra high dimensional, but not as much as these low dimensional and high dimensional techniques. Okay, again, our focus will be in this tutorial on low dimensional data sets and high dimensional data sets. And at this point, I'm going to give the mic to Arnab, who is going to explain the state-of-the-art techniques in low dimensional data. And after that, I'll come back and explain for high dimensional data. Any questions till now while we switch? Any questions? Okay, seeing none.
Yeah, there are no questions as of now, so we can continue with the next aspects.
All right. So thank you to the organizers, and thank you, Parth, for this wonderful introduction to these things. So I will now go over some of these low dimensional nearest neighbor indexing methods. They are also exact in the sense that since they are in low dimensions, we can afford to find the exact nearest neighbor. We need not go for approximation. But let's just jump into it. So most of these low dimensional nearest neighbor things can be fitted into this hierarchical framework. So I will first explain the framework in generic terms instead of taking any particular index structure. So we assume that there are this data set of n objects in some d-dimensional vector space, and each object is represented by a hyperdimensional bounding geometric convex box. Now, what do I mean by that is if a point, if the object is just a simple point, then the bounding box is by itself. However, in many applications, the object may not be just a simple point. It may be a spatial object. For example, when you are searching for restaurants, etc., or let's say a playground is not a point. It has a spatial dimension around it. In any such case, I mean, so we can always bound that spatial object within a nice tight little box, right? That is what we call these minimum bounding boxes. So these are so each object is now just a minimum bounding box. And these boxes are then organized in a hierarchy. So it's a step-by-step thing. And so the only requirement that we have for this generic framework is that if there is a box at level I, which is a larger box, it must completely encompass all the smaller boxes. So please do note what the requirement is that a larger box must completely encompass all the smaller boxes. Notably, I am not saying that the smaller boxes need to be disjoint or the larger boxes need to be disjoint or any such thing. The only requirement is this should be completely encompassing. I am not even specifying that this structure, that the hierarchy has to be balanced. But of course, making a balanced structure improves performance. So all the index structures are actually balanced. They actually try to achieve this balance, but that is not a requirement per se. So basically, then we have this hierarchy of structures. The root, the top of the hierarchy contains everything, right? That's the entire space of things. That is, so if you're indexing, let's say, spatial objects in a city, the root will contain everything in the city, right? And then that root will be divided into smaller boxes, correct? And now this idea of this on memory versus on disk things comes, is that traditionally databases came from this disk-based settings, and even now, because the data sets are so large, not every memory can hold it. So when you are accessing data from a disk, that is being accessed in a disk page manner. This is very similar to the OS page things, right? You cannot access just a simple byte. You have to access that entire page. So the databases took this view that, okay, let me see, when I'm bringing in a disk, I should be able to utilize the space requirements of the disk completely. So so the design is disk by disk, and the top level, so any box is divided into M boxes such that those M boxes fit in a disk page, right? So that number M is the largest number that fits in the disk page, okay? So now, if the total number of objects is n, as we said, and then M boxes fit in each page, therefore the total number of leaves, so each leaf is a disk page, that is n by m, right? And now, for this n by m leaves in the last but one level is then organized into n by m, right? So n by m squared, and so on and so forth. Right? So the total number of bounding boxes is order n by m, which is linear. So the size overhead of the index structure is linear. So this is another important thing, is that if you have let's say a 10 gigabyte data and a 1000 gigabyte index, then that may be problematic. But here it is just linear. And the height is just log n base m. And because the height is this thing, and this is the traditional B plus T thing, so any object can be located in at most h disk accesses. Okay, all right. So here is a concrete example. Of course, it's a toy example, but here is this. So this entire structure is called an object pyramid, as you can see, because there are more things in the bottom, and finally you just reach the pinnacle, which is the entire thing. So T is the entire object set here. T is divided into, let's say, two boxes, 1 and 2. So this top part is 1 and the bottom part is 2. 1 is in turn divided into A, B, and C, capital A, B, and C, which contains these small points A, B, C, D, all these things. So this structure is called an object pyramid. And this provides a multi-resolution representation of the database objects, right? You can look at it at any resolution. If you look at the topmost resolution, then everything is one. If you look at the bottommost, then every point is, or every object is looked at separately, and anything in between. So now, having this framework in mind, we can fit in the structures, okay? So B plus tree, this is the traditional thing in databases. Almost every database uses it for indexing, etc. B plus tree is only for one-dimensional objects. This came as a variety from B tree. And the internal nodes do not contain any pointers. Only the leaf levels contain any pointers. This is a recap of the basic database stuff. And the B plus tree node, the final, so essentially these are child pointers, the CP0 to CPK, and then there is a key. So the key is the value which divides this entire range. So remember, because B plus tree is one-dimensional objects, so essentially the entire range of keys, the entire domain of keys is the single number line, right? So it's just one number line. So if you put a number, if you put a key one, then that divides into two parts. Everything less than equal to that and everything greater than that. Now, if you put in k such keys, then it divides into k plus one children nodes, child nodes. That's the basic idea. Fair enough. So, and how is this key, this number k determined? As I said, is the largest k that can fit into one disk page. Okay, fine, fair enough. Okay. Now let's see, let's jump into this KNN queries a little bit. So how do we actually do the KNN queries? Remember, this is not an exact point search. I'm not searching that point exactly. I try to find the k nearest neighbors. So there is a query point q and a positive integer k that I want to find k nearest neighbors of it. And what it is being done is that a heap, or the max heap of k current estimates are maintained, right? Estimates. So first of all, it is just an estimate. And what happens is the generic strategy is the following thing is, as you explore more and more into the B plus tree structure or any structure into the database, you change these estimates of this, right? And at some point in time, the estimate becomes actual values, because then you can actually find a distance to a thing. And when you see that the estimate of any other object in the database is greater than the distance that I have already found, this is a maxi, right? The maximum distance that I have already found, then I'm sure that I do not need to process these other objects any further. And I have already have my answers in the maxi. So that's the basic idea. Again, we'll go over an example, but this is just a basic idea. So here is an example. So we go back to that the structure, the toy example that I had. And suppose this is a point Q, as you can see, and I want to find two nearest neighbors. So the answers are J and D, right? I mean, this is just because by visual inspection, I can tell you that the answers are J and D. But let's see how it will be actually found. So you start from T, because that's the root, and well, you have no other answers. And at some point in time, you descend into either 1 or 2. Now, because Q is in 2, you will estimate that the answers are from this box 2 and not from 1. Okay. And then, so you will descend into box 2, and then within box 2, again, you will descend into box D, because D is closer than E, because this is inside. Okay? And within D, you will now search, and your current estimates will be I and J. Remember, why is the current estimate I and J? Because you have only descended up to D. Now you have these actual distances to I and J, so that is your current estimates. But now you will go back and say that, okay, E may have a distance lesser than my distance to I. The I is the second largest distance, right? So then you explore E, and then you explore B, and then you finally do this correctly. But that's the idea, is that so you do not explore more than what you need, but and you maintain this estimate. Okay, fair enough. Now this KNN searching order. Now, so what we did, we searched into some D, and then I and J, and then E, and then B, etc. So that is a KNN searching order. Now the efficiency will depend very, very heavily on in which way these children are being searched. So the traditional two ways of going over an tree from the traditional algorithms perspective is the depth first search and the breadth first search. However, in databases, in this searching, what is being done is neither depth first search nor breadth first search, but it is called best first search. The best first search is because it is maintaining a priority queue and a heap of things. So it will explore anything that can give you the best estimate at that point in time. It need not be strictly depth first or breadth first, right? So here is just a complete example. In interest of time, I will not go over entirely of these things, but just to give you an idea. So at the current time, the first thing is that the priority queue contains only T. The estimate is 0 because this is within T, right? And I have not found any answers. Then, well, I cannot find anything from T, so I extract from T the two nodes, 1 and 2, and then estimate. I mean, then put in their estimate of the value. So 2 is 0. The estimate of distance to the box 2 is 0 because Q is within 2. And with 1 is, let's say, 4, some distance now. And then I always keep on extracting from the best position of the heap, which is 2. So now I extract 2 and insert D and E. Then I extract D and then I insert HIJ. And now you see it goes into this random fashion, right? And then I extract E and then put K and L. Then I extract 1. So you see, so you first extracted 2, then D, then E, then 1, right? So it is neither depth first nor breadth first. This is best first search. And you keep on doing this. And finally, you have this, you start getting actual answers about this point J. So when you have this J6, so that is your first answer. And then you extract D and that is your second answer. So you start getting answers at this thing. And you see, you also maintain the distance to the second, I mean, the kth nearest neighbor, that is 8. And at this point in time, you can stop because anything on the heap is greater than 8. So by expanding CA, any of these things, you cannot get a distance less than 8. And you have already found distances up to 8. So at this point in time, the whole process stops. So as you see, this is not exploring everything. So for example, it has not explored C at all. It has not explored A at all. And it has not gone into K and L and H and this. So it tries to optimize this. It is not exploring all the things. And that is the whole point. Because if it is exploring all the points, then it is a order n search and then a linear search is no worse. Right? Fine. So now with this framework in mind, let us go into some actual structures, actual multidimensional structures. So the most important multidimensional structure is the R tree. This is a family of things. So the R tree is, remember in B plus tree, what happens is that this is a single dimensional, I mean, the keys are single dimensional. Instead in R tree, these are actually D-dimensional. Now, what happens in R tree is that you can take some of these points and can enclose it in a larger box. That is what our generic framework tells you, right? So this larger box is called a minimum bounding rectangle. For example, if I take this small a and small b, this small a and small b, that can be enclosed in this tight box, which I am calling the large A, capital A. Right? Then C, D, and E can be again put into another tighter box. This is the capital B, and so on and so forth. So this entire structure, you again get this entire structure like this. Very importantly, so each thing is, each box is represented by 2D parameters. Why? Because there are D dimensionals and you need to mention the lowest point and the highest point. So that's 2D parameters, right? Fine. So now you can also intuitively see that if D keeps on increasing to high dimensions, this becomes problematic, right? So if D is 100, then you have 200 parameters for each box and so on and so forth. And now you see why intuitively R trees cannot work for very, very high dimensions. But for small dimensions, this is fine. Also, importantly, there's a concept called dead space. Dead space meaning the space where there is nothing important, no object. So within a city, there may be places where there is nothing important. No tourist wants to go there. There is no restaurant, no mall, nothing like that. So you don't even worry about it. So the dead space, R trees are very nice in the sense that they don't care about dead space. So they will not index dead space. Okay. Also, children may overlap, and children are overlapping. As you see, 1 and 2 are overlapping here. A and B are overlapping here. C, of course, does not overlap. So it may overlap, may not overlap. That does not because it may overlap, now the question comes is that when you are trying to search a point or trying to find the nearest neighbor, etc., that answer may be in multiple children. So there is a whole way of efficiency decides on which children do you explore first and so on and so forth. Right? But the structure of the R tree node is very similar to the B plus tree node. Instead of a single key, they have these 2D parameter keys. And then there is a underflow parameter and overflow parameter. It must get at least that many children, at most that many children, and so on. And the disk page capacity, so there is a very easy way of finding out what will be the fan out of this R tree, how many children can fit into this. The reason I am saying this is that, you see, C is constant. C is the disk page capacity. So typically, let's say this is 4 kilobytes or 8 kilobytes, something like that, right? Now, beta is the fan out that you want to do. And this gamma and eta are also constants, right? Because let's say these are 8 bytes, etc. Now, this D is problematic, right? Now, as D increases, this fan out decreases, right? This is from very, this. So now if D keeps on increasing, then this fan out will keep on decreasing. And finally, it may happen that there are maybe only 2 or 3 keys that fit into this, or even less than that. Then it does not make sense to use an R tree because it's not reducing much. So this D directly comes, the dimensionality directly comes into the design of the R tree. So for very large Ds, it is obvious now that it cannot sustain arbitrarily large Ds. Okay, definitely not in the tune of millions or any such thing. Great. Okay, and for R trees, there are multiple extensions. R star tree, this is some engineering optimizations. R plus tree, they break the objects such that the children do not overlap. That is the design choice. Then there is this very nice set of ideas called SS tree and SR tree. They say that, oh, why this have to be minimum bounding boxes and why not minimum bounding spheres? Fair enough. So you can use them and you can get other kind of structures. So here the idea is that instead of one box encompassing all the other boxes, a larger sphere must encompass all the other spheres. But that's the same idea. Then there is this A tree which quantizes the boundaries such that you use. Now the 2D parameters may actually require 2D into 8 bytes, right? But if you quantize, let's say it takes 2 bits, that is a huge saving. So you can pack in more things. But that's kind of the idea. As you see, R tree and R star tree has been there for decades now. And many of these things are very old in the sense that because at that point in time, most of the applications were using low dimensional things. And then they cared about exact things. Nowadays, of course, we have these very high dimensional things, and therefore we have moved into this approximate nearest neighbor paradigm. Okay. Just to finish these low dimensional things, there are 2 very, very important structures. These are ideas that you should be knowing. One is one is called the Quadtree. Right? So the Quadtree idea is that it's a 2-dimensional thing. Let's say that means if you put a point A, then you can break it up into 4 quadrants, right? So if you put a point A here, that breaks up the space into this first quadrant, second quadrant, third and fourth quadrant. And in turn, each of them can be put a point again. And so if we put a point in this first quadrant B, then it breaks up into these things and so on and so forth. So you can have these things. So these are point quadtrees. They are memory-based structures. They are not guaranteed to be balanced, but that's about quadtrees. And then there is another thing which is called KD tree. The KD trees do not break it up into quadrants. It always breaks it up into 2 parts, but it does it dimension by dimension. So it splits only 1 dimension at a time. So for example, if it takes that A as the point, it first uses dimension 0 to break. That means that entire dimension 0 has been broken up into 2 parts. And then it recycles among the dimensions. So in this one part, now it uses dimension 1 to break out. And then again dimension 0, then again dimension 1 and so on and so forth. So first is dimension 0, it breaks A, then in dimension 1 across D, then dimension 0 again, then dimension 1 again. So it does it. So again, these are not guaranteed to be balanced, etc. And these are on memory things. Fine. So these are just the references, and I will now hand over to Parth back. But if there are questions, please you can ask now. Otherwise,
there are a couple of questions in the Q&A.
Okay, the Q&A, just 1 second. I'm just trying.
I can start off with Raja's question about trade-off for creating an artery for 10 dimensions compared to running a linear search to get nearest neighbors when our data is in the range of 10,000. And
right. Okay, so let me just answer this. So arteries, the traditional thing, it starts breaking out around 10 dimensions. So anything more than 10 dimensions, arteries start breaking down. I mean, so start breaking down in the sense that linear search starts winning over arteries. Up to 5 or 8 arteries are definitely better for most of the applications. But that is, so these are all fuzzy boundaries, right? So 2 to 5, definitely arteries better. 5 to 8 or 5 to 10 it's not clear. After 10, it starts because it goes into this high dimensional space.
And if I were to add, it's also about the cardinality of the data set. That means how many points do you have? Absolutely. And if you have a really fast CPU for Euclidean distance for 10 dimensions for 10,000 points, you might even get away with doing a nearest neighbor search, brute search,
force, linear search.
Brute force. But again, it depends on how many times do you want to do the query processing.
Yes.
So there are many factors that do deal with on how do you want to proceed. And I think that's a really great question that I feel that many sometimes miss when either you're doing an overkill of the technique that you want to use, or you're going to do an underkill based on the scenario. So I think that's a really good question.
Right. In fact, it is being said that when you are doing an exact nearest neighbor search, one of the benchmarks must be linear search. If you have not done a benchmark with linear search, I don't believe your method.
Absolutely. And if the cardinality is in millions or billions, I think we can fairly say with a good probability that our tree will fare better, because it's going to prune a lot of points to look at in order to find the nearest neighbors.
Okay, other question. Okay, I can see now the questions. Okay. So on the current presentation by Professor Arnav, do we know the keys to be used beforehand, or the keys need to be determined from the set of attributes? If they are to be determined, what are the ways of doing it? Very good question. No, we do not need the keys to be done. So this is the traditional insertion method that we do. So in a B plus tree, so best way of understanding about R trees is to think that this is a generalization of B plus tree. Now in a B plus tree, when you start getting keys, what do? You start inserting them, and in some point in time, you decide on how to split, right? Into 2 parts, on which key to split, right? Similarly, for a binary search tree, let's say, but binary search tree is much more degenerate. In a B plus tree, so then you decide, and then you keep on inserting, right? And then if these leaves are overflowing, then the height of the tree increases by 1. Otherwise, you adjust, and so on and so forth, right? So R trees have these very similar things, and then there is a whole process of how to insert and all those things. In fact, this R star tree that is on the slides now, these are these engineering optimizations of our R tree. So R star tree is not a new design or not a new idea per se. They do these optimizations. These are engineering optimizations on how exactly to split, how exactly to when to insert, and how how to manage these parameters, etc. That is why they perform better in practice than R tree. But we do not, I assume we do not know the keys. If there are other questions you may ask.
There's one more.
Yeah. Okay. There is one more question. Are there any recent advancements on the KNN algorithms? I mean, if I understand the question, of course there are. That is what we will now, next parts will tell you all the recent advancements. I told you about the older advancements. So the recent advancements parts will now tell you. But R tree is, you cannot not know R tree if you know indexing, right? So that's why it is very important structure. Just to go back to the one question. So if you know the distribution of keys, so for example, if you know the set of keys beforehand, then there is a process called bulk loading in databases, which means that now you can organize this much better than just keep on inserting them one by one. So there are bulk loading methods like STR and other things, which will give you a much better R tree. Now, when I say much better R-tree, what does it mean to be much better? Does it look good? Well, it gives you better efficiency when you're searching things, right? So it's, see, the more spaced apart these children are, the better the search efficiency becomes better. So if you already know the set of keys or their distribution, then you can do much better. You can use that information. But it is not required to know that. That's what. I guess any more questions we can take it up, or in the interest of time, we can move ahead.
Okay, answer the question.
Thank you. Question. Okay, I will stop sharing.
Thank you, Arnab. Thank you for introducing the traditional nearest neighbor techniques for low dimensional data.
But there's just, sorry, one more question. How do we fight cuts of dimensionality here?
Right
so
here.
That is what we are going to see now. That is what we are going to see now.
I'm going to talk about how to deal with cuts of dimensionality in this talk, in this part of the tutorial. Thank you. Okay, so thank you. And again, to reiterate, the goal of the tutorial is really to explain, to give more knowledge to the audience as to, given the specific scenario that you may face, and what are the decision-making process steps to figure out what technique you should be using. And for Ragja's question, there was a decision on the cardinality and the dimensionality, and right now I'll explain the techniques for high dimension data. What happens if you have high dimension data? Okay, alrighty. So as I had mentioned, the traditional hierarchical structures suffer from the curse of dimensionality, where what happens is eventually even a brute force search is faster than using these hierarchical structures. So one way to avoid the curse of dimensionality and to avoid looking for exact results and instead look for approximate results. And there are two main benefits to this. One is obviously this is a trade-off, that if you accept a small loss in the accuracy, then it results in a really big performance benefit. And the second really important point is, in high dimensional spaces, these approximate searches are oftentimes good enough. And what I mean by good enough is, these distances do not have much meaning as these dimensions increase. And because of this, if you are talking about distances in tens of thousands, then if you have 2 points and a query point where you're talking about distance of 10,001 and 10,004, then there's not much difference between them. So if you were to return, if an approximate technique were to result a point with 10,004 distance as opposed to 10,001, you will probably get similar results. And what do I mean by that is, again, if you have low dimensions, a range query for returning these interesting points of locations within a 5-mile radius, that query makes sense. But if you have really large distances, and distances will be large, again, it depends on how dense your data is, but it's also on how many dimensions that you are dealing with. So we have these are really two popular real world data sets. One is the famous audio data set that includes these, for each audio file, it uses an audio feature extraction algorithm to represent the given audio file as a 192 feature vector. And for that, for these 50 random queries, in order to find the 100th nearest neighbor, the distance is 7,000. And for another data set with completely different dimensionality, the average distance for finding the 100th nearest neighbor is 2,000. So in these cases, what is found is that in these cases, instead of these range queries, it's better to have a nearest neighbor query. Is you do not know, for if I were to contrast it with nearest locations, I'm as a user who's using some map application, I know that I want everything in 5-mile radius. But given some high dimensional data set, not knowing the density or the sparsity of the data set, you do not know what the range query, what should be your range query. And hence, for that, for high dimensional data sets especially, it is much more beneficial to find k nearest neighbors instead of predefining a range query saying, give me points that are within 1,000 range or 10,000 range, which does not have much meaning. So from here on, I will explain these techniques that deal with the k nearest neighbor problem, which is also abbreviated as KNN. And in order, again, that sometimes approximate results are more beneficial because of the trade-off between accuracy and performance. In order to formally define it, this problem is called the KNN problem, where, as you can see here, is if this is the radius of a query, then the KNN problem says that, you know what, I will accept any results that are within CR radius. Okay, so in the interest of time, in the interest of a really good performance, I am okay with getting some inaccurate results where a point which is inside CR versus a point which is inside R are probably going to give you similar results. Okay, and this C is usually a user-defined approximation ratio, which with nowadays, with state-of-the-art techniques, there are many techniques that even for C is equal to as low as 1.2, gave really good, accurate results while saving a lot of time. Okay, and since I mentioned that KNN is much more beneficial, the KNN problem is easily generalized to the KNN problem, and that's what we'll be focusing on in this part of the tutorial. Okay, so obviously when Arnab was explaining the low dimensional data sets, there were exact results. So really the evaluation metrics would be, as he mentioned, what is the index size, or how fast did you finish the query. But now, since we are dealing with some loss of accuracy, you need some more evaluation metrics apart from the traditional index size and the query performance time. And for that, for these accuracy metrics, in order to assess the quality of your of the result, there are two popular evaluation metrics. One is called the approximation ratio, which is different from the C that I mentioned. I know they're really annoying because they have similar names. And the second one is the mean average precision. And I'll explain briefly what they do. So basically the approximation ratio is saying that given I will find the ground truth of my queries by averaging the ratio of these distances. So I will given a query point and the ground truth. The ground truth is the actual answers that are if your distance measure is, let's say, Euclidean distance, then for 100 nearest neighbors, I will do a brute force and I will find these 100 true nearest neighbors. And then I will find the Euclidean distance of the result that you had given and return the average of the ratio of the distances. So the benefit in here is, again, it is recognizing the fact that I'm okay with having a ratio of 1.1 because that is still giving me nearby answers, and I'm not looking for the exact ratio of 1.0. And the second one, which is more popular nowadays, especially in the machine learning community, is this average precision. And what average precision takes into consideration is the order of the results. So the approximation ratio does not take care into consideration the order of the results that you are getting. So, but average precision states that, hey, if you are getting, let's say, this point as the most nearby candidate in your technique, then, and if in reality it was the 90th point, then this has to be penalized and this has to be taken into consideration by your technique. Okay, these are the two main evaluation criteria used in these approximate results. Okay, and there's one question, say, asking what do you mean by approximate results, and whether an exact result, whether result will miss in your answer. And the answer is yes. Is as I mentioned that if I give you an image of a cat, and if you have two images of a cat and they're both similar to the query image, it's really difficult to say that one is better than the other. And approximate results takes this into consideration and saying that if I were to find a distance, if I were to create a distance between these two images, then I'm okay. Even though I rank one image as better than the other, approximate results are saying that I'm okay as a user. I'm okay with being returned the second image as well. Okay, and that's the whole idea of approximate results. Okay, any other questions? I hope that answers the question on approximate results. So there are many different KNN techniques nowadays, and we decide to categorize them based on these categories. That first we talk about external memory based and in-memory based, and then in-memory based. But please note that there are many crossovers nowadays, and I will just give just mention some names of these crossovers in the next few slides. But now I'm going to talk about, just give brief ideas of these different techniques, these categories of techniques, and give the pros and cons of each of these techniques, with the hope that by the end you can say that if I'm given these criteria for my application, then I can with a certain probability say that I should be using data independent techniques like random hashing. Okay, ready. So let's begin. And I'm going to start with random hashing methods, which is really popular. Locality sensitive hashing, which is a random hashing method. And by random hashing method, I mean that they are data independent techniques. That means that when I am creating the index structure, I am not looking at the data distribution. So many techniques, especially in the machine learning community, and I will mention a few afterwards, they would create these index structures that are more efficient for that particular data distribution. And I'll explain the pros and cons of that approach as well. Random hashing methods say that I don't care about the data distribution, but I'm going to create these hash functions such that the idea is that similar data points are mapped to the same hash bucket with a higher probability than dissimilar data points. And to give a very quick example, so think about this is my query point, and I have only I have two data points in my database, X and Y. Locality sensitive hashing says that I will randomly have a hash projection through this space. So then I will map these points to the hash function. And now obviously I cheated with a really good examples such that Q and X are mapped to the same bucket. So if you see these are buckets of a hash function, similar to hash maps that all of us have learned in our basic computer science classes. So next question is, what would happen if I have point over here? I believe I was calling it Z. So it will also map to the same bucket. So how do we try to avoid this? And what locality sensitive hashing says is that I will use multiple of these hash projections such that false positives and false negatives are reduced. So for H2, again, Q and X will probably map to this bucket, whereas Y will again be mapped to a different bucket, but also Z, that is the point here, will probably be mapped to another bucket. So what locality sensitive hashing says is that I will use a collection of these hash projections to get an answer. And so the question would be, how do you create these hash functions? And this is one formula for creating the hash function for the Euclidean distance. Different distances have different hash function families. To just give an overview of what this is again, W is the width of these buckets. O is my data point as a vector. So X is a vector, and A is this random vector that I multiply with O to create these hash functions, these random hash functions, with B as a random shift on top of that. Okay, again, this is an overview of LSH. And one important thing to note that since what I mentioned right now, that was the original classic E2 LSH, but there are multiple improvements, many improvements over the year that has improved as to how do you choose W, how is there any other better way of creating hash functions, and so on and so forth. So one thing, since we've been working in this domain, one thing I will say that many people from different domains use locality sensitive hashing, and I often see that they still use the classic E2 LSH, but I would suggest anyone who's trying, who wants to compare with LSH, to consider using more advanced LSH techniques than the classic E2 LSH. Okay. I have to go with the example again. So what are the benefits and disadvantages? So benefits, one really important benefit is that LSH gives theoretical guarantees on your problem, on the result set, saying that if the user puts in an acceptable success probability, then LSH will say that if you were to create these number of hash functions, then for this amount of data that you give me, your result set will be, your recall, for instance, will be at least 1 minus the accepted error probability. Okay, So for security applications where you don't want to risk loss of accuracy, or applications like that, LSH is really useful. And another important thing is due to the simplicity of its of the technique, it has really fast, efficient external memory implementations. And I will explain some more techniques which are in-memory techniques. And when you have data in billions, which is very common nowadays, then external memory implementations are much more useful. But again, the disadvantage is that it's a data independent technique. So when I'm creating these hash functions, I don't know, I don't care about the data, I guess I can say. And hence it results in lower accuracy when compared with some state-of-the-art data dependent techniques that I will mention in the next few slides. Okay, ready. So, excuse me. So the question is, so how do, excuse me, what happens for data dependent techniques is, so there are these category of techniques called learning to hash methods. And there are again hundreds of papers in this field, where the goal is that these hash functions basically should be created such that the data distribution has to be taken into consideration. Okay, so obviously, like in several machine learning techniques, since you're learning from the data, you need training data and you need some sample queries in order to create these hash functions. And so these hash functions are based, there are multiple different papers. It can be on linear projections, kernels, deep neural networks, and so on and so forth, that help in figuring out what should be your hash function. So this is a very commonly used linear hash function. Again, where W is this projection vector and B is the bias variable. So the only thing I want to mention, show here, is that there are methods, there are hashing methods that take into consideration the data distribution while creating these while creating these hash functions. So then, is this always going to be better than LSH? And again, this is this depends on your application. Is it in memory or external memory? While majority of these learning to hash methods are focused on in-memory processing, there are recently some papers that have started to show external memory implementations for these trained learning to hash methods as well. Okay, and so obviously the benefit is higher accuracy since you are learning the hash functions. You will get better accuracy, and disadvantages are, obviously you need training data. So what if you don't have training data available? What do you do? That's, I guess, a problem with all machine learning techniques, if I can say that. And obviously the indexing is slower because you have to have the training phase and then index the data. And most importantly is it's not very efficient for dynamic settings. Is what happens if your data distribution changes? Then obviously your hash functions may change. Then you'll have to re-index the entire data set. So there is always a trade-off in these nearest neighbor techniques. Okay, and so I'm going to go a little bit faster. There's another technique called HT index, which is a recent paper published at PVLDB, where Arnab is a co-author. And it uses these RDB trees so basically which are modified B plus trees that uses Hilbert keys. I'm not going to go into much details, but the paper shows that it is better than current techniques like LSH. So the benefits are that it's really scalable. It gives really high accuracy, but since it is using some hierarchical structure, the accuracy is the accuracy is a little lower when the dimensions are more than 100. So it is much better than the R-tree. But if you have dimensions in 1000 in thousands, then the HG index will not perform as well as some other techniques. Okay, and I'm going to explain two important categories after this. One is called the vector quantization based methods, where product quantization and its successors they use compression and clustering techniques to reduce the memory footprint and speed up the query processing. And again, the benefit of product quantization and OPQ and other methods is the index sizes are really small. And the disadvantages I'll explain in the next category is that the accuracy of more state-of-the-art techniques is better than product quantization, but index sizes are really small. So if you are really constrained on the amount of memory that you have, then in that case, you should use product quantization and these relevant techniques. Okay, and lastly, the group of recently using proximity graphs, and the idea behind proximity graphs, graph-based techniques is to use these navigable small world graphs. And if I'm these images are borrowed from previous slides, and the goal is that these are the points in your database, and you want to create these graphs such that you create these long links between these points with the hope that when you have this query, when you have the query point here, and even if you start somewhere else, then using these long links in the graph, you should find your nearest neighbors very quickly. And recent papers, HNSW, which is hierarchical navigable small world graph, and other similar techniques have shown that they are the fastest state-of-the-art ANN techniques. The disadvantages are that there is no theoretical guarantee that LSH or random hashing gives. And since it's a graph, there are a lack of external memory implementation. So you need a large memory if you were to deal with really large data sets. Okay, so I hope that this these overviews of these different categories of techniques in the high dimensional domain gives you the advantages and disadvantages of different techniques that are built for different application scenarios, and that this is a good starting point, that whatever data scenario that you face, you are more equipped with making a better decision on what technique to use. Any questions? We have about 15 minutes remaining, and we have only one slide on research challenges. But any questions before that on high dimensional techniques?
Yeah, there is a question from Supratim, and
Okay,
does dimensionality reduction method such as JL is useful?
Yeah.
Dimensionality. So great question, Supratim. So dimensionality reduction, obviously. So LSH kind of does dimensionality reduction. They are useful certainly um, in uh, changing in lowering the dimension space. But obviously you need some techniques on how to find nearest neighbors after that. And the techniques that I explained are really about how do you deal with finding these nearest neighbors? How do you prune all these data points and only look at the nearby candidates, and while giving theoretical guarantees or not, while looking at external memory implementation versus uh, in-memory implementation and etc. Okay, so I hope so. Sometimes they're orthogonal. There's a question, comment.
No, just to add to Supratim's question. See, so this JL lemma is for Euclidean distances, and it reduces into this log n dimensions kind of thing, right? So when n is very large, this log n is still not to guarantee something. You require log n, right? Now this LSH also can be viewed as a dimensionality reduction method where you can control the space where you reduce it to.
Yes.
By
using multiple hash projections.
Lesser than log n, and so if the goal is just to reduce dimensionality, then there is a separate way of looking at things. But LSH also enables you to do the next problem, which is the NN problem, much better.
Yes.
Amit has a question which was also there, which is regarding updates, insertions, deletions, and in general, a data stream kind of scenario where the points are changing rapidly.
So excellent question, and I think one important thing to note is dynamic settings are really important nowadays. So it depends on how your data distribution is going to be affected by these insertions and deletions. So if you do not know, and if you want to play safe, then LSH, since again it's a simple technique, that would be the easiest one to extend it to dynamic settings. There are several papers that use, there are some papers that use LSM trees, which are popular indexing structures for dynamic settings, for insertions and deletions. So it again depends on how your data distribution is going to change. If you're confident that the data distribution is not going to be changed drastically, then and if you want higher accuracy, then you can go with these learning to hash methods. But if you do not know with how your data distribution is going to be affected, then it's safer to play by using locality sensitive hashing.
Right. So just to add, so this LS, so the learning to hash is just like with any ML thing. Once you have learned and then new data comes, there is not much that you can do unless you do a lot of other techniques, RL and all those things. So you have to relearn. So these are not very good for update things. LSH per se is very good because you get a point and you hash it. Then this, the hierarchical structures, say HD index and these kind of things, these are essentially B+ trees, so which are very naturally update friendly. So that can also work. But the graph methods can also suffer because the graph may change drastically because of these insertions. So
yes.
This HNSW, etc. may.
Yes.
But this is a very, very important point actually. Yeah.
Yes. So excellent question. If I were to jump in, basically.
Can you also add a little bit on, spatiotemporal kind of indexing, in the sense in the specific domain of spatiotemporality, where cars are moving around or people are moving around and you want to find nearest neighbors. How are these techniques, dynamic techniques, useful?
So I can take a stab at that. So basically, for spatial applications, there are many papers that deal with moving objects. How do you make quadtrees and other KD trees structures really more efficient for really, really fast updating. It's not that much addressed for high dimensional techniques, and this is what we mentioned in these research challenges is especially external memory based techniques. There's not a lot of work done for these incremental and dynamic data scenarios, but for spatial applications, for 2D 3D applications where your objects are constantly moving, where your KNN queries, the KNN results are constantly being updated. There is a lot of work in that domain. Okay, so to finish our presentation again we mentioned some of the research challenges that we see for the next few few years. And one thing is when I mentioned ultra high dimensional nearest neighbors, there are several papers, not as much as the for high dimensional nearest neighbors, but um, uh, how can we have efficient external memory implementations for really ultra high dimensional nearest neighbor problems. The second challenge we see is while there are many theoretical guarantees, techniques that guarantee accuracy in terms of recall, there are none that give a guarantee on the mean average precision of the result set. Additionally, we talked about NN techniques for Euclidean distance, but what if you have where it's for LP distances, P is not equal to 2? What if you have 1.5? So there are some papers on it, but not many. Like lazy LSH is one popular technique, but not many in that domain. And again, in our discussion, as we mentioned, in what happens if you have incremental and dynamic data scenarios? What are the effects on the graph for proximity graph based techniques? What about for OPQ or product quantization based techniques? How is that clustering affected? Does the centroid change, and will that make a difference? So these are still many problems that need to be addressed. And lastly, in this new learning to index uh, category of papers, the goal is basically, can we use machine learning to improve the search? And that's again, I think we think that it's a hot topic, and many challenges are still there in that domain. And with that, again, thank you for attending this tutorial, and we'll be happy to take any more questions.
So I do not see further questions. And yeah. So one question that I have is, the machine learning techniques, as Arnab was mentioning, they work very well for static kind of environments. But for dynamic environments, there is reinforcement learning also. So, so the question that that comes up is, two things. One thing is many times machine learning techniques can work reasonably well for non-numerical data also, right? And whereas for numerical data for very high dimensions, the notion of nearest neighbor also goes for a toss because of curse of dimensionality and other things. So the question is, um, uh, are there some analysis which was done on at least for non-numerical data, how well this nearest neighbor kind of techniques work?
I think this is a very, very good question. I do not think I have seen anything that works with non-numerical data, so categorical data and all those things. Especially what does even a nearest neighbor mean? It's very hard to define there, right?
Right.
Yeah. So, but yeah, I think that's another unanswered question. In fact, I don't think anybody has even tried to.
No,
Path
so
maybe.
the see, one of these days is that there is some notion of some partial similarity measures being given to some of the data, right? And then you learn from that and then try to find whether other data sets are similar to this data.
Right.
Right.
Those things can be there. So that is, so there are two things to it. So the semi-supervised is one of these things, right? So where you have some information and then you try to complete the other information. This can also happen for some of the attributes you have. I mean, so you have a distance, what you say, I mean, some similarity measure for some of the attributes, for the rest you do not know. Then you try to fill up. Those can be done because, I mean, I saw some of this in some other context of some other database queries, not per se after using them. These are for ranking kind of thing. So,
okay.
Yeah, but not really, I mean, a matured work in this nearest neighbor domain. I am not aware, at least. I've not seen. But,
okay. I do not see any more questions. And yeah, and then if the participants have questions, we can take them. And I'm happy that there are a good number of participants in this tutorial.
Yes. Yeah, it's a very good opportunity for us also. So, I mean, I'd like to thank everybody.
Yeah. Okay. Okay, then. Thank you very much. And I think we are done.
Okay.
Yeah. Fine. Bye.
Thank you, everyone.
Bye.
Thank you.
Thank you. Thank you. Bye.